Welcome back. Problem 6-191. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Materials by R.C. Hibbeler. Statement is determine the shear and moment in the beam as a function of x, where x is greater than 0 and less than 6 feet. Draw the shear and moment diagram for the beam. So you can see this is the cantilever beam, clear, where there is a point load at this end which is 8 kips. At a length of 4 feet, we have clockwise movement of 50 kips into feet, and there is a distributed load from fixed end till the length of 6 feet, and the magnitude is 2 kips per feet. So we have to determine the shear and moment equation in term of x for the region x is greater than 0 and less than 6 feet, and then we will draw the shear force and bending moment diagram. So let's start with the solution. If we remove this fixed support at this end, so we will be having a reaction force. Let this is your point number 1. So there will be reaction force which is R1, and there will be a moment as well. Clear? So this we will find this R1 and M1 by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point 1 is equal to 0, and taking the counterclockwise moment as positive. So about this point 1, one moment will be due to this 8 kips load, and the perpendicular distance is this 10 feet. And this is producing clockwise movement, so it will be negative. So I will write minus 8 into 10. The second moment is this one, which is 50 kips per feet into feet, and this is again clockwise, so it will be also negative. So minus 50. Now you can see you have a distributed load. So we will convert this distributed load into a point load. So for that, we will multiply this 2 kips per feet with the length over which it acts. So 2 into 6, which is 12. And this load is acting downward, and that will be acting at a half of the total length. The total length is 6 feet over which this distribution load acts, and the half will be 3 feet. Okay, so the third moment will be due to this 12 kips load, and perpendicular distance is 3, and this is also producing clockwise movement, so it will be negative. So I will write minus 12 into 3. And the last moment is this reaction moment, which is counterclockwise M1, and that will be positive. But the sum of all moment about point 1 must be equal to 0. So from here we will get M1 minus 80 minus 50 minus 36 is equal to 0, and we will get this M1 will be equal to 166 kips into feet. So this is the reaction moment when you remove this fixed support. Now we'll find this R1 by using equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So R1 is upward, 12 is downward, that will be minus, and minus 8 will be, their sum must be equal to 0. So R1 minus 12 minus 8 is equal to 0. So it means that R1 is equal to 20 kips. Now you have R1 and moment M1. So what we will do is that we will section this beam in the range of x is greater than or equal to 0 and less than 6 feet, and draw the free body diagram. So if I draw it over here, let this is the beam. This is point 1 where we have a reaction force R1. R1 is 20 kips, and the moment was, we calculated, is 166 kips into feet, that is counterclockwise. And this length which we have cut the beam is x, and there is a distributed load over a length of x, and this distributed load is downward. So when you convert this distributed load into point load, so it will be acting at the mid, clear, and the magnitude of this distributed load is 2 kips per feet. So this point load will be equal to 2 into x, and that will act at a half of the x. So this will be equal to x by 2, and the remaining will be also x by 2. And when you cut the beam, you will be having a shear force that will be, we will take it downward, V, and you will be having a reaction moment M. So we'll find this V and M in term of x. How we'll find this? So by using equation of, let this is point O. So we'll find this M and V by using equation of equilibrium. This equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So 20 is upward, minus 2x is downward, and minus v, their sum must be equal to 0. So 20 minus 2x minus v is equal to 0. So from here we will get v is equal to 20 minus 2x, and the unit will be in kips. This is your shear force. Let this is equation number 1, which is the equation of shear in term of x, and this is for region x is greater than or equal to 0 and less than 6 feet, where we have cut the beam. Now we will find this moment by using equation of equilibrium, that sum of all moment about point O is equal to 0 and taking the counterclockwise moment as positive. So about this point O, the first movement will be due to this 2x and perpendicular distance is x by 2, and this is producing clockwise movement, so it will be positive. So I will write 2x into perpendicular distance is x by 2. The second movement will be due to this 20 kips load and perpendicular distance is x, and this is producing clockwise, so it will be negative. So I will write minus 20 into x. The third moment is this 166, that is clockwise, counterclockwise movement, so it will be plus. So I will write plus 166, and the last movement is external movement, which is considered as counterclockwise, so it will be also positive, and their sum must be equal to 0. So from here you will get m plus x square, because 2x into x by 2 will be x square, minus 20x plus 166 is equal to 0. So this moment equation will be equal to minus x square plus 20x and minus 116, and the unit will be kips into feet, and this is equation number 2. So equation number 1 and 2 are shear force and bending moment equations in term of x, and here you will use x is greater than 0 and less than 6 feet. Clear? So this is the answer of our first part. Now we'll move toward drawing the shear force and bending moment diagram. So for what we will do is that we will take the vertical line from the end of this beam, and first we will draw the shear force. So for shear force I will take a horizontal line to show length x in feet, and on y-axis we have shear force and unit will be kip. Clear? So what, let one division is equal to 5, so 5 plus 10 plus 15 and plus 20, and similarly downward that is minus. Okay, so for region of, if I draw a table, clear, and the table will be like that, x value shear force in kips and moment will be kip into feet. So for x is equal to 0, you can put it in this equation number 1. So when you put x is equal to 0, this v will be equal to 20. So I will write v will be equal to 20 kips. And for x is equal to 0, so this will be 0, this will be 0, and moment will be minus 166. So I will write minus 166. Similarly, for region of x is 6 feet, so if you put x is equal to 6 feet, so it will be minus 12. So 20 minus 12 will be equal to 8 plus 8. So V will be plus 8. Similarly, you put x is equal to 6 feet in this equation and you will get movement will be equal to minus 82. Okay. So for x is equal to 0, we have V is equal to 20. So what we will do is that for x is equal to 0, our first point is this one. Clear? And for x is equal to 6 feet, so this is 6 feet length. We have shear force is 8 plus 8. So we will locate plus 8. So plus 8 will be somewhere here. Let me choose the point. This will be plus 8. Now you can see that shear this loading is a uniformly distributed load or load with a horizontal line and of 0 degree. So shear force will be 1 degree higher as the load is downward. So it will be a linear, the shear force will be a linear line and slope will be decreasing. So we will join these 2 points using straight line. So this will be the loading. Now in moving from this point till this point, we do not have any other force, so shear force will remain horizontal. So it will be remain horizontal till the end, and at the end you can see you have minus 8 downwards, so that will cause it toward downward 0. Clear? So this will be your shear force diagram. Now we'll draw the bending moment diagram. So for bending moment diagram, I take the horizontal line to show the length x in feet, and on y-axis we will having moment that will be unit kips into feet. Let one division is of 100, so minus 100, minus 150 and minus 200. So for x is equal to 0, we have moment is equal to minus 166. So minus 166, let minus 166 is this point. This is minus 166. And for x is equal to 6, we have moment is minus 82. So let minus 82 is this point. Minus 82 is this point. Minus 82 kips into feet. Now you can see that shear force is a linear line with slope decreasing. So bending moment will be second degree curve and it will be in clockwise. Rotation will be in clockwise direction. So we'll join these 2 points by using a curve. Okay. At this point, you can see you have external movement of 50 kips into feet, that is clockwise. So while drawing in bending moment diagram, it will cause the bending moment to go upward. This is convention given in the book. So minus 82 plus 50 will be equal to minus 32. So bending moment will change to minus 32. So let this point is minus 32. So your bending moment will change toward this. Okay. And the last one is this area under the shear force diagram, and you can see this area is, this height is 8 multiplied by length is 4. So 8 fours are 32. So minus 32 plus 32 will be equal to 0 at this point. So you will get the shear bending moment 0 at this point. And we will join these 2 points using a straight line. Clear? And that will be your bending moment diagram, and which is the answer of our second part. So that was all about problem 6-191, in which first we solved the shear force and bending moment equation in term of x, and then we draw the shear force diagram and bending moment diagram. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.